All right, we're recording properties of exponents today. And so last time we looked at what is an exponent. We looked at how do they function, the base, the exponent, how does that work. Today we're going to be looking at applying those some different properties of those exponents and how we can combine exponents together. We're looking at three different properties today. So three and a half different properties today. The first one that we're going to be looking at, if we have 5 to the third power times 5 to the second power, 5 cubed times 5 squared. The way we want to look at this is, and I guess our goal, what we're trying to get to, is we're going to try and have an answer of 5 to the something power. We want to get it down so it's just one base and one exponent, and that's our goal. And so if we look at this and we think about it, 5 to the third power is 5 times 5 times 5. 5 to the second power. 5 to the second power is 5 times 5. So if we do 5 to the third times 5 to the second, we've got 5 times 5 times 5 times 5 times 5. And that breaks down into 5, a base of 5, big number of 5, multiplied by itself 5 times as a factor of 5. And so our final answer then becomes 5 to the fifth power. The base of 5 being multiplied by itself a factor of 5 times, 5 to the fifth. Now, that's a long way to do it. That will always work. You can always what's called expand this out. So you can expand them out and then count. 1, 2, 3, 4, 5. 5 to the fifth. And that will always work. Of course, if you had something like 5 to the 500th times 5 to the 23rd, that would take a very long time. And so a method, an algorithm, a way to get the answer without doing the expansion part in between is to simply add the exponents together. If you have 5 to the third times 5 to the second, 5 cubed times 5 squared, you can simply do 5 to the 3 plus 2. You can add those exponents together and get a final result of 5 to the fifth. And that's a method that we can have to work with these exponents. So we have this here, and you have it on yours to multiply with powers of the same base, and that's important. Multiplying powers with the same base. If they don't have the same base, this doesn't work. And we'll see examples of that in a little bit. But if they have the same big number, the same base, we keep the base and add those exponents together. And this is your general form of that, b to the m times b to the n, where b is some base, m and n are some exponent. The final result is you can add those exponents together. And we saw that with the way it expanded out. Okay, so try these two on your own. Or pause it, try them on your own, and then I'll come back and we'll do them together. I'm going to assume you tried it on your own. So we've got 6 to the 6th times 6 to the 3rd. If I broke it apart and expanded it, I'd have 6 sixes here and 3 sixes there, and I would end up with 6 plus 3, which follows our algorithm to get 6 to the 9th power. So 6 to the 9th power would be 9 sixes total, and that would be your final answer. I only need to see this as work. You don't need to show this step in here. I'm going to show it for now, simply so I can communicate that, but you don't need to show this. There's really very little work that you need to show. You just need to write the answer. So end of the 5th times end of the 7th then. We'd have 5 ends here and 7 ends there, so we'd have end of the 5th. We can add those exponents together to follow our algorithm, and we end up with n to the 12th power. And that would be our final answer. Okay, give these 4 a try, and we'll see what you come up with. I assume you paused it and tried it on your own. For that first one, same idea. We've got 4 to the 2nd times 4 to the 4th. Big number stays the same. The base stays the same. I add those exponents together, 4 to the 6th. 2 to the 5th times 2 for C. 2 to the 5th times 2. Now in this case, we've got an exponent for 5, but no exponent there. However, if we expand this, we'd have 5 2's all being multiplied together. And here, we would have just 1 2. So really, this is like having 2 to the 1th, 2 to the 1 power. There's 1 2. I can see it. It's right there. And so it'd be 2 to the 1st power. And so if you follow the algorithm, it'd be 2 to the 5 plus 1, which would give you 2 to the 6th power total. And again, if you expand it, it works out to the same way. 1, 2, 3, 4, 5, 6 2's all together. And so we would have that expanded version working as well. But the algorithm does work. 2 to the 5th times 2 to the 1th, 2 to the 1, and so we'd have 2 to the 6th total. Next one, B, x to the 2nd times x to the 3rd. Again, if we use our algorithm, 2 plus 3 is 5, x to the 5th. For D, we've got x to the 5th times y to the 2nd. If you got something to the 7th power, you did something wrong. If I expand this, I'd have 5 x's and I'd have 2 y's. The problem is the bases aren't the same, which means that there's nothing we can do to combine these together. And that came from our definition back here as well. I even circled it. They have to have the same base. If they don't have the same big number, then we can't combine them together. And our final answer, what I would ask you to write down on a homework assignment, or what I would ask you to write down on a test, is just rewriting the problem over again. That's as simplified as it can get. We can't get that any simpler. X squared times x to the 3rd, for this one, we can get that simpler. We can break that, or we can combine that together and simplify it to x to the 5th. For D, x to the 5th times y to the 2nd, we can't simplify that any further. We're stuck with x to the 5th times y squared. All right, moving on here. And so we've got division. So division with exponents. Again, the same base, the same big number, 3. I expand these out. We've got 8 3's, 6, 7, 8 3's all being multiplied together. And in the denominator, I've got 3 3's being multiplied together. If I want to simplify this, and some of you, I'm sure, have already looked down below and see the algorithm, but let's look at why this works. If we've got 8 3's in the numerator, 3 3's in the denominator. If I divide 3 divided by 3, 3 divided by 3, that's just 1. Again, 3 divided by 3, 3 divided by 3, well, that's 1. 3 divided by 3, that's 1. So what I've got left is 1 times 1 times 1, and then I've got 1, 2, 3, 4, 5 3's left over. And so 1 times 1 times 1, that doesn't really affect anything. It's just 1. And 1 times anything is still anything. So 3 times 2 times 2 times 3, 3 to the 5th power, and those 1's just don't affect it. So 3 to the 8th times 3 to the 3rd, or excuse me, divided by 3 to the 3rd gives us 3 to the 5th, which shows right down here with our rule. If you have any big number b divided by any big number b with an exponent of m or n, you can simplify by subtracting those exponents away from each other. And this is why it works. I'm showing you up on the top here why that works. You don't have to show the expansion every time, but that's why that happens. That's why we can subtract, which works out pretty well, actually. The multiplication, when you're multiplying powers, you add those exponents together. When you're dividing with exponents, you subtract the powers. That's fairly easy to not to mix up. But this is why it works. So we subtract those exponents. Okay, take a minute, pause it, try these 4 on your own. Assume you paused it and tried it on your own. Again, if we use our algorithm, we should have 7 to the 5th minus 3, because we're subtracting these exponents away from each other. We get 7 to the 2nd power. The next one, 9 to, well, I'm going to go to C, sorry, C, 9 to the 9th divided by 9 to the 2nd. So again, if I follow my algorithm, I'm going to subtract 9 to the 7th power. For B down here, I've got x to the 10th divided by x to the 9th. 10 minus 9 gives me an exponent of 1, or you could just write x. Both of those would be acceptable. Both of those are correct. The 1 is always there, the exponent of 1. We just don't always write it. But if you do, if you want to write that 1 there to remind yourself of what happened, do it. Both of those are correct. And for D, e to the 10th divided by e to the 5th, if we subtract, we're going to end up with e to the 5th. 10 minus 5 is 5. So that's our final answer. And that's all the work I would have to see, is the answer. Almost done. This is our third. So there's going to be 3.5 different properties. This is our third property of exponents. When you have an exponent inside parentheses with another exponent. This is a little bit different. This is not 6 squared times 6 to the 4th. So we don't add these together. This is 6 squared to the 4th power. I apologize about that. I don't know what happened, but we're going to go with it. 6 squared, and then we have to the 4th power. What this works out, if you expand it, we get 6 squared times 6 squared times 6 squared times 6 squared. 6 squared is the base. So the base is 6 squared. The exponent is 4. So it's 6 squared as a factor 4 times. Now we have a rule. Now it's multiplication. 6 to the second times 6 to the second. 6. We're going to add those exponents together. 2 plus 2 plus 2 plus 2. And again, you could expand this further and show how many 6s there would end up being. But if you add those together, 2, 4, 6, 8, we get 6 to the 8th power. There's got to be a faster way, right, than expanding that all out. That seems like way too much time. In fact, there is a nice handy rule. If you are multiplying, if you have an exponent raised to another power, 6 squared raised to another power, what you're going to do, and I'm going to go ahead and have you write this because it doesn't seem to be showing up the way I had intended, is we're going to use that big B, or the little b, I guess, but our big base B to the m power, parentheses, to the nth power. So if you have those parentheses with a power raised to another power, we're going to multiply those exponents together, m times n. And that works out for this first one as well. 6 squared to the 4th power, 2 times 4 does give us 6 to the 8th power. So our power raised to another power, we multiply. And that's what it says right here, and it shows that then. With our example, 9 to the 4th to the 5th, we multiply to get 9 to the 20th, and it does show it right there. Okay, try these 4 on your own, and we'll come back. I'm going to assume you tried it. So, first one, 5 to the 4th power raised to the 2nd power. If I multiply those exponents together, 5 to the 8th. For C, 3 to the 3rd to the 4th power. If I multiply those together, I don't add, remember, so that can give me 7. I'm going to multiply, I'm going to get 3 to the 12th power. For B, I've got 6 to the 7th to the 9th. So if I multiply those exponents together, I'm going to get 6 to the 63rd power. That's a big number. I don't know if your calculator could even handle it. Try it, see if it does. 4 to the 8th to the 2nd power. Again, I multiply those exponents together. 4 to the 16th power. Okay, so our 3 rules so far. We've had multiplication. You add the exponents when you're multiplying with the same base. We've got division. With the same base, we subtract the exponents. And a power raised to another power, we multiply those exponents together. The last, I'm calling it a half of a property. The last thing that we're going to look at is what happens when the exponent is 0. It'd be 6 multiplied by itself 0 times, which makes absolutely no sense. It just doesn't, that's hard to think about. There is a way to prove what this equals, and if you ask me in class, it doesn't take long. It's not that confusing. I'll show you how that works. But the answer ends up being 1. Anything to the 0 power is 1. It's always 1. Doesn't matter how big the number is. 500 billion to the 0 power is 1. 11 billion, which is Miss Greenfield's favorite number, to the 0 power is 1. And so if you will write this down, please, x to the 0 power equals 1. Any number to the 0 power will always be 1. And while that doesn't make sense intuitively, it doesn't just obviously make sense, anything to the 0 power equals 1, there is a fairly easy way to show it. But if you ask me in class, I'll be happy to show you why that works. All right, last thing that we do, we've got, I think, do you have 6 questions or 8 questions? 8 questions here, actually 6. 6 questions. Give these 6 a try, and then we'll look at them together. Okay, here we go. So, last 6 questions here. End of the 3rd times end of the 4th. Since it's multiplying and they have the same base, we add those exponents together, end of the 7th power. For the next one, again, same base, 10 and 10. They're dividing, so we subtract those exponents, we get end of the 4th. For number 2 down here, it's a little bit backwards. That's all right. For number 2, 8 times 8 to the 8th power. Again, there's always a little 1 there, even though we don't always write it. So if we add those exponents together, 8 to the 9th power. Don't forget about that little 1 exponent that doesn't always show up. Fourth problem, again, we're dividing, same base, t and t, t. And so if we subtract 9 minus 7, is going to give us t to the 2nd power, t squared. And the last two here, m to the 2nd power to the 19th power. So again, we're going to multiply those exponents together, and we're going to end up with m to the 38th power. That's a big M. Last one, 10 to the 4th to the 0 power. Now, again, we're going to multiply. So if we multiply 4 times 0, we get 10 to the 0. But we know that anything to the 0 power always gives us 1. And so if you just wrote 10 to the 0, that would be wrong, because that's not as simplified as we can get it. We can get it simpler. 1 is simpler than 10 to the 0. So you have to get, if it's anything to the 0 power, we have to get it all the way down to 1. Okay, that's it for this lesson, and good luck.